Hello everyone, section 4.4, congruence and transformations. Example 1, identify any congruent figures in the coordinate plane and explain. So we have triangle ABC, AC is 2, BC is 1, triangle PQR, PR is 2, QR is 1, and this is diagonal, this is a right triangle, this is a right triangle, but this is twice as big as these two are. So which two triangles are congruent? Triangle ABC is congruent to triangle PQR. Now, how can I do that without proving the triangles are congruent, which is something we're going to do in chapter 5. We can prove it with transformations. So A can be mapped to P by a translation of 1, 2, 3, 4, 5 to the right and 1 up. Now if I move A to the 5 to the right and 1 up, I have to move C 5 to the right and 1 up. 1, 2, 3, 4, 5 and 1 up. C lands on R. B needs to move 5 to the right, 1 up. 1, 2, 3, 4, 5 and 1 up. B lands on Q. They map to each other. They are congruent. Example 2. Describe a congruence transformation that maps quadrilateral ABCD to quadrilateral PQRS. So if we look at ABCD, and right now it's mostly in the bottom left-hand quadrant, it's quadrant 3, a little bit in quadrant 4, and PQRS is mostly in quadrant 4, but a little bit in quadrant 1. If I rotate ABCD 90 degrees, then ABCD is now mostly in quadrant 4 and a little bit in quadrant 1. Now let's go back and look at coordinates. P is at 3, 1. A prime would be at 3, 1 after a 90-degree rotation. Q is at 5, 1. B prime would be at 5, 1. 1, 2, 3, 4, 5, 1. Matching up, and I can do this with every single coordinate. S is at 2, negative 1. D is at 2, negative 1. R is at 5, negative 3. C is at 5, negative 3. And they match up. So 90-degree rotation about the origin gets them to land on each other. Example 3. In the diagram, a reflection maps line P or segment PQ to segment P prime Q prime. A reflection in line B maps P prime Q prime to P double prime Q double prime. Also PJ, which is right here, is 3 units, and LP double prime, which is right here, is 8 units. So we have some questions to answer. Name any segments congruent to segment PQ. So PQ is congruent to P prime Q prime and P double prime Q double prime. So P prime Q prime and P double prime Q double prime. Any segments congruent to PJ? Well, yeah, PJ is congruent to P prime J, P prime J, which I think is a little bit different on the answer key. It does say P prime J prime. J prime's the same point as J. It's just not written in this diagram here. But J and J prime are the same point because they're both on the line of reflection. I showed you before. That's like the mirror and the fingers touching each other. QK, so QK is the same as Q prime K prime, or Q prime K, Q prime K. Okay, so that's the answer to part A. Part B, JK is equal to LM. true or not true and explain if they are. Well, A and B are parallel to each other. This is a right angle. This is a right angle. They correspond to each other, which is proving that they're parallel, but it also helps that we have the arrows to indicate that they're parallel. Q double prime, Q prime, and Q prime, Q double prime, they have to be right angles, again, because it wouldn't be a reflection if this line A wasn't the perpendicular bisector of Q prime. So line A is the perpendicular bisector of Q prime. So this is a right angle, this is a right angle. That makes quadrilateral JKML a rectangle. What do we know about rectangles? Opposite sides are congruent. So yes. Does the measure of segment JK equal the measure of segment LM? Yes. Why? For the reasons I just said. It's a rectangle. And why is it a rectangle? For the reasons I just said. All right. What is the length of P, segment P double prime? So from P to P double prime. Well, A is the perpendicular bisector of P prime, so that makes this 3 units. And B is the perpendicular bisector of P prime, P double prime, so that makes this 8 units. 8 plus 8 is 16. 16 plus 6 is 22. There's the answer to example 3C. Example 4. In the diagram, the figure is reflected in line K. The image is then reflected in line M. Describe a single transformation that maps the figure F to F double prime. So here's F. It gets reflected in line K, making it F prime. F prime gets reflected in line M, making it F double prime. These two lines are intersecting lines. And according to the theorem, reflections in intersecting lines, this single transformation could be done by rotating F around the point of intersection, P, to F double prime, and the angle formed by the two intersecting lines is half the angle of rotation. So let's go end to end. This angle here is twice as big as 58 degrees. So that angle will be a rotation. So that's a rotation. Rotation of 116 degrees, twice 58, about point P. About means around. Geometry textbooks, we always use the word about point P. Okay. Example 5. What type of transformation has the same effect as each composition of transformations? So this may seem complicated at first and may look like I'm looking for a bunch of math to be done. I'm actually just looking for the name of the transformation that has the same effect as the composition of transformations. So we have a translation followed by a reflection. What single transformation does that? That would be a glide reflection. Okay, here we have a translation followed by another translation. What single transformation does that? Well, instead of doing a translation this way and then a translation this way, I can do a single translation that brings me from the beginning to the end. Translation. Okay, reflection in the line y equals 7, and then in the line y equals 3. So the key here is we're doing a composition of reflections in two lines. Now what's true about these two lines? These two lines are parallel. So this goes back to the reflection in parallel lines theorem. A reflection in two lines that are parallel could be done as a single translation. And that refers back to example 3. PQ is reflected to P prime Q prime. P prime Q prime is reflected to P double prime Q double prime. Lines A and B are parallel to each other, so PQ could have been translated to P double prime Q double prime instead of two reflections. Part D, reflection in the line y equals x, and then in the line y equals 2x plus 5. What's true about these two lines is that they are not parallel, they are intersecting lines. They do not have the same slope. A reflection in two intersecting lines is a rotation. And that's the end of section 11.4, 4.4. Thank you very much. Bye.